and you should see a notification. So all right, looks like we're good. Okay. So we're going to go ahead and get started. I'm going to share my screen, which apparently we can't say anymore without. Okay. So tonight we're going to be talking about what is volunteer monitoring and why does it matter? Jesse and Jordan are going to be doing most of the talking tonight, and they'll introduce themselves. My name is Ann Lewis. I'm the Special Projects Coordinator at the South Dakota Discovery Center. And I will be kicking off here. So before we go into the nitty gritty of what we're talking about, I just wanted to start with this overview. And let's see if I could get this to advance. Okay. Just a quick overview on the agenda. We'll have a few minutes of welcome and housekeeping. I want to talk a little bit about volunteer citizen science and the Clean Water Act. I have a what is a TMDL demo, and then I'll toss the ball over to Jesse and Jordan, and then we'll circle back around and do questions and wrap up. So citizen science, what is that? It is, you can see there the broad definition, and I won't read it to you verbatim, but the idea is you have volunteers, people who are not paid to be scientists, contributing information to research. And specifically for our purposes, this is a water quality monitoring citizen science project. And you've all done this all summer long. Volunteers collect water quality data, and it will be used for the scientific management of lakes, rivers, and streams, or to support the Clean Water Act requirements. And what makes it a citizen science project is that you are following protocols set by DANR, which is the agency responsible for maintaining and protecting water quality. So let's just talk very briefly about volunteers in the Clean Water Act. In 1972, the Clean Water Act was established, and it required states to clean up the water. Prior to that, there was legislation and things in place, but there wasn't a lot of enforcement involved. So it did things like set uniform water quality standards or required states to set water quality standards that were approved by the EPA. It required states to make a plan on how water quality goals would be achieved. And then states had to submit biannual reports to the EPA on the status of lakes, rivers, and streams. And so there were, up until 2002 or so, there were two reports, the 305B and the 303D, I believe, which talked about the condition of lakes, rivers, and streams, and then identified impaired waters that required TMDL development. And so these reports were integrated, and now they're presented as one. And this is where our data comes in as volunteers. Volunteers help provide data for this work. Now I'm going to toss it over to Jesse and Jordan here, but first I wanted to do a short little demo on what is a TMDL. That is one of those things that's tossed around a lot in water quality circles, but I wanted to show you this. This is my homemade TMDL measure maker. It's not a real thing, but I'm just using this as sort of as a stand-in. And what you see here is a pretend assessment tool. So this down here, this pole is the measuring of of lake and river water quality. And so as long as the measurements of the pollution that is going into the rivers and stream is here in the green, I don't know if you can see, that's supposed to be green. The total maximum daily load of pollution going in there is fine. But once that load of pollution pulls the water quality readings down in here, Jesse and Jordan and everybody else has to write away a plan to reduce the total maximum daily load of pollution going into the water so it stays here. So that is sort of my brief Water Festival version explanation of what is a TMDL, because it's not super intuitive. So with that, I'm going to toss it over to Jesse and Jordan and let them take it from here.
Thanks, Ann. Right. Does that look okay? All right. So I'm going to walk you through just a couple slides of background on the WQMAP website or mapping application. The full name is the Water Quality Monitoring Access Portal. So I found a way to make WQMAP the acronym for that, and I was happy about that. A little background here. So you probably looked at it by now. If you haven't, that image there is kind of what the website looks like. It's a lot of dots and then a lot of rivers and lakes, and all that, everything that shows up represents data, and mostly, water quality data. And so like, whose data is this? Well, it's DANR's, it's projects that we fund, like watershed projects. It's data collected by water development districts, by volunteers, by cities, and there's some from the U.S. Geological Survey. So it comes from a lot of different sources. How much data are we talking about here? Well, when I tallied it up the last time in 2018, shortly after we created the website, it was about 3,600 monitoring stations with about 140,000 water chemistry samples. Those are the kind of samples that you collect where you go fill up a bottle from the lake or the stream. And then there's some other data too. There's algae data from looking at the algae cells and counting how many of each species are there. There's elutriate samples. Those are things like heavy metals and sediment and PCBs and sediment and things like that. And then there's about 8,500 fish flesh samples. The majority of those are mercury samples, but then there's also heavy metal samples and things like that, where they analyze the fish flesh and see if there's, toxic bad stuff in it. When I tallied this up, I made a rough estimate of how much that data was worth just in lab costs. It was about $20 million. And as you know from doing sampling, there's a lot of time and travel involved. And then there's also a lot of equipment involved, especially for us when we use multimeters and other fancy equipment to make measurements. So this data is worth a ton of money. And all the data that you see there, the website links directly to our central water quality database, which is, central to our program and our agency. It's what all of our work revolves around. Scientists can't do much without data. And then there's a lot of other information here too that you may have seen. Information from the Integrated Report on Surface Water Quality, which is a publication we put out every 2 years. It includes those lists that Ann mentioned, the 305B list and the 303D list. That's kind of a list of the impaired waters in the state and whether the state in general is meeting water quality standards. There's information about active implementation and water quality assessment projects. Implementation projects are like restoration projects where we go in and try and clean up the mess. There's links to TMDL reports like Ann was talking about and other watershed project reports. And Jordan and I do write TMDLs. That's part of our job. There's watershed strategic plans, and then there's a whole bunch of old water quality documents. I went through all the old bookshelves in the office in Pierre, and I found every old document that was on there. I had them scanned and I uploaded them. So there's stuff going back to the 70s and 80s, early 80s in there that you can find too. And it was interesting to me because you'll find examples where like I went to high school in Watertown and everybody always says that, oh, they messed up the lake when they plugged up the outlet that was by the airport. So I always thought that that was interesting. So I dug through all the old reports. There was never an outlet up by the airport. In fact, the Big Sioux River wasn't even connected to the lake really. So that's kind of the things that you can kind of figure out from those old reports. It's kind of interesting. There's all that fish flesh data. Well, that's my son there, Henry, with the trout. South Dakota Game Fish and Parks collects most of the fish flesh data when they do their fish netting. And a lot of it's mercury. And like I mentioned, there's some other metals, there's some PCB data, things like that, bad stuff that you don't want in your food. And okay, let's just get into the website. And there we go. So this is what it looks like when you open it up. I'm going to move a couple things around here. There's always this disclaimer. I have to put that there. So I just close that. You can read it if you want. And then the help menu is automatically open. I think that this is a great thing because I wrote this help menu, and it's not the only reason I think it's great, but there's a lot of good information in here, not only to understand how to navigate the website, but how to help interpret the graphs and the data and the other information that's available there. So if you have any questions at all, I encourage you to read the help menu. And that gets opened up by this little question mark up here. So if you have questions, refer to help. And then there's a couple other buttons up here. And let's start with the legend. We'll go through what all the stuff on the map means. And you see all the dots. The yellow dots are chemistry samples. The orange dots are citizens monitoring samples. And you might think that that's your data, but it's actually not. It's the old volunteer program, Dakota Water Watch, that was run through East Dakota Water Development District. I've thought about trying to get your dots changed over to orange dots, and I may do that to make it easier for you to find your data. But I didn't want your data lumped in with that other old data because your data is of higher quality. So I kind of wanted to keep that separate. That was the reason that I split them out to different colors in the first place, because yours is of a higher level of quality than theirs. And so I put yours alongside ours in the yellow dots. And then the green dots are where GF&P collects fish and fish flesh for that, contaminant analysis. You'll also notice that a lot of the streams are red or blue. Well, they're all either red or blue. But what does that mean? The red streams are impaired. That means they're on the 303D list of impaired waters, and the blue ones are not. The same thing applies to the lakes, and you can't really see so well when we're zoomed in out like this, but we'll zoom in here in just a minute and you'll see the lakes are either red or blue as well. And that gives you an idea very quickly of whether or not your water body that you're interested in is meeting its water quality standards. So the other button here, the one in the middle, this is the layers. This is how you turn the different data layers on and off. And they're exactly that, they're layers, they're laid over one another. And so you can turn the streams on and off, and you can turn the lakes on and off. This all other NHD rivers, what that is if you zoom way in, it'll show you where the drainages are with little blue lines. Oh, it's turned off. There they are. So you can see which way the water's flowing, or if there's a little tiny stream there at all. And then there's some roads, and then another, I'm gonna use the home button there to go back to our home zoom. And there's this lake region button here, or layer. And that's going to come into play further down the road in our discussion here. But what that does is it really splits the lakes up into regions so that we can compare lakes that are similar to one another. So we've got the Black Hills region, we've got the Western Plains in green, we've got the Eastern Lakes in red, and then the Northeastern Lakes that are primarily up on the Coteau in blue over there. And we'll come back to that several times here. So how do we look at our water body? There's a couple ways to do it. You can just zoom in, like that. You can use the roller on your mouse, or you can use these buttons here, or you can use the search bar. And the search bar here is pretty helpful. If you click the drop down arrow, you can pick what specific things you're searching for, or you can just leave it as all. I'm going to pick lakes here. I'm going to go to Lake Poinsett. We've got some good examples there. And it takes you right to Lake Ponset, and it gives you this little pop-up menu here, pop-up window with 4 different links in it. And if we click Water Quality Dashboard, that opens up another page. And if it takes too long here, I was planning ahead and I actually opened this beforehand, because sometimes they take a little while, because like I mentioned, it's querying a database with 140,000 some records in it. It takes a little while sometimes. So there it popped up. And what we see here, this is the water quality dashboard, and it's a series of graphs representing our water quality data. And so the first graph here is total nitrogen. And you can see there's the squiggly line running through. And what that is, it's a moving average of all the lakes right here in the Northeast Lakes region. You can turn it on and off right there. And so that gives you an idea of how your data compares to, the rest of the lakes in the region. But that's not the only way you can compare. There's these stats up here at the top. And you can look at these numbers to compare your lake to similar lakes. So the Lake Ponset mean is the same thing as average. The mean is 1.395 for nitrogen. Well, Lake Ponset is in the Northeast Lake region. The regional average for lakes in this region is 1.922. So we see that the Lake Ponset, compared to other similar lakes in the Northeast, has a lower nitrogen concentration, which is a good thing for Lake Ponset. It means it's probably going to be a little cleaner. Looking at the lake median and the regional median, this is the central number, so the middle number. So if you're looking at 0 to 100, it would be 50, or 0 to 10, it would be 5, just whatever number's in the middle. And it's a good measure of kind of like the average. It's a good measure to look at. And again, here we're lower for the lake median than we are for the regional median. So we can see how Ponset compares to other similar lakes. And then there's also the maximum and the minimum, which I think are less useful. But the maximum in particular can be useful because you can see, like, how bad does it get here? How bad does it get in the region? And so if we go through these graphs, oh, one other thing, if you hover over these dots, you can see the actual result. Now, if we go to phosphorus, same general idea. We see that the lake, in terms of phosphorus, the mean or average is a little bit lower than the regional mean. In this case, the median, though, is a little bit higher than the regional mean. So we would say, okay, well, on average, it's a little lower, but by the median, it's a little bit higher. So Ponset's probably pretty typical or average for the region in terms of phosphorus. And again, the squiggly line is the moving average. We go over here to chlorophyll. And so chlorophyll is our measure of, it's a measure of how much algae is in the water. Again, we can see that Lake Ponset is doing pretty darn good compared to its neighbors in the Northeast lakes. And so the whole idea here is to be able to compare your lake to other lakes. Let's move over to E. coli. Now, this one's a little different. We don't have a moving average line that's on here automatically. Instead, we have 2 other lines. And these are the 2 water quality standards for E. coli for Lake Ponset for the immersion recreation beneficial use. Oops, I turned that one off. The single sample max, the green one, is the one that we care about the most, because when we do our sampling, we're doing single samples and we don't sample enough to address this blue line. That's the 30-day geometric mean. You have to have 5 samples collected within 30 days. And the geometric mean, not just the average, but the geometric mean has to be below this blue line. We're going to turn that off because we're not going to worry about that because we're not sampling frequently enough to even address that standard. So we're really just going to worry about the single sample maximums. And you can see here on Ponset, back on May 25th in 2016, that it had an E. coli concentration of 517. That was well above the single sample maximum here, standard of about, 235, I think. And so, but we can see also that since then, we had one high one in 2017, but not over the standard. It's still okay. And then as we go, we see that it's been low the last few years. 1 second, please. Hey, Jared, would you go open the door? My apologies. I had to take my kids with me to the office today because my wife had to work late. She's a nurse and she's just got here to pick them up. All right, we got one more tab here. And this is the transparency or SecuDisc measurement. As if you've been sampling lakes, you've seen this before. And these are all the results. Again, the squiggly line is the moving average. And we can compare our values to the region. And we see this is one of those measurements that we want to be high because it's a measure of how clear the water is. So we see that Lake Poncet is higher on average or by the mean than other lakes in the Northeast region. So that's the idea of these graphs for lakes. Now you'll also notice here on the dashboard, there's these links across the top here. Those are the same links as you see on this pop-up window. We'll go back here and I'm just going to walk you through these real quick. Support status, this is whether or not the lake is meeting its water quality standards. And when we say whether or not it's meeting its water quality standards, what that really means is it's supporting its beneficial uses, because each beneficial use, which they're listed here, has standards associated with it. And we'll show you those in a little while when Jordan's doing a little her talk later. And you can see that there's not supported. That means that it's impaired, the impairment parameter, for mercury and fish tissue. So that is why Lake Poncet is red on the map. If it has an impairment that would be in this column, that would make it red on the map. If there's none here, it would make it blue. We can also see the year of assessment because we created the website in late 2017, 2018. That's when we just started compiling this information here. The plan is to keep adding these every 2 years as new integrated reports are released. And because we assess the waters every 2 years, that's why we release the report every 2 years. So in 2022, next spring, we'll have a whole nother batch of these here. And it may have impairments, or impairments may go away if our data shows that it's no longer impaired. The next tab over here on the top is monitoring data. This is a really useful little tab or part of the website because it gives a list of every sampling station on the lake. And there's quite a few of them here. These SWLAZZZ ones, these are mine for statewide lake assessment. That's what SWLA stands for. That's one of the programs I run here at DANR. But if we go back up here, we see LPA. These 5 stations are the Lake Poncet Association stations. And if we click on view data, it gives us a nice little pop-up table with a selection of the results. And pretty much all your results are going to show up on here because I picked the most important parameters for lakes to display on this table. So you can see the results here, the TKN, the total Kjeldahl nitrogen, ammonia, nitrate, nitrite. TP is total phosphorus. There's no E. coli here because this is the central lake site where we don't collect E. coli. You can see a chlorophyll result. So another thing that I want to show you though, clicking on this link here where it says view data, it does the exact same thing as clicking on the dots on the map. Here, I'm going to find that same station. I think it must be this one. There we go. There it is. If you click view download monitoring data, it's the same table as we were just looking at in the monitoring data tab. So there's 2 different ways to get to this table, but there's also one other thing here that's important. If you click download all parameters here and you have Microsoft Excel on your computer, which I just clicked, it will download all the data, not just these parameters that are listed here, but everything that we got for that station going back to the very beginning of when we started sampling water quality data in South Dakota. Basically, if we have data for it, you'll get it by clicking on that button. And because Lake Poncet Association started sampling in 2021, that's all that's here. But you'll get this Excel table and it's got all this stuff. So if you really want to dive deep, this is how you do it. But we'll leave that for another time. If you click access all water body info, that takes you back to the dashboard. So this is kind of circular in nature. You can get to the same place multiple ways, and then you can get back to where you started again. So there's one more tab here, projects and reports. If we click on that, it says there's no active projects found. That's not entirely true because we have the rotating basin project going in the Big Sioux Basin, but that one just didn't get added on there in time. TMDL reports. Here we can get links to the 2 TMDL reports that we have associated with Lake Ponset. The statewide mercury TMDL and a TMDL for nutrients that was written for Ponset a long time ago. You click on those links, it opens up the document as a PDF. This one's pretty old, it's from 96. But there's some interesting stuff in these old reports. So if you're curious, take a look at it. Oh, where was I? That one. And then project reports. These are all those old documents that I found off the shelves. 1988, 1999. There's all kinds of old stuff in here. I'm not going to get into that right now, but if you're curious, go ahead, dig through that old stuff on whatever water body you're interested in. All right. So that's how to look at a lake. Streams are just a little bit different, but not that much. So I'm going to zoom out here. I just use my mouse roller. And there's those lake regions again. So as you think about Lake Ponset, you're comparing it to all the lakes in this blue part. Let's go to the Big Sioux River segment 8 down here south of Del Rapids. And just like you can, I don't think I really said it, but you can click on a lake or a river, and that's how you get to the dashboard, just like if you search for it and it pops up. So if we click on the river here, Big Sioux, that 08 means segment 8. It's the same menu. So we'll click on the water quality dashboard. And this is really similar, except for we just have a little bit different parameters at the top here. Most are the same, but not quite exactly. So we've got nitrogen, but we don't have a moving average because we don't have a region to compare it. Like we did a lot of work to figure out those lake regions to make proper comparisons. We don't have anything like that at this time for the rivers and streams. Phosphorus, same story. There's a lot of data here on this part of the river. It's getting sampled a lot. I believe volunteers are sampling it. The East Dakota Water Development District sampling it. DANR is sampling it. But at least you get these basic statistics. So these can kind of give you some info. You could compare the mean and median of one stream to another to give you an idea of which one is cleaner. On the total suspended solids graph, we do have 2 lines here again. These are the standards. And again, we mostly worry about the single sample maximum standard. That's the top one. The bottom one here, again, it's a 30-day average standard. It's a little bit different than the E. coli, but you'd have to collect 3 samples within a 30-day period, and the average of those samples would need to be below this blue line. Again, you guys don't usually sample that frequently to where you're going to be able to assess those kind of standards. So we're just going to worry about that single sample maximum. And as we look here, we see that there's a pretty healthy amount of dots over that line. And so there's a good chance that this one is listed as impaired. If 10% of the samples are over that single sample maximum, then it's going to be considered impaired. And we'll check in just a second here on the support tab. And so E. coli, we still have our 2 standards, just like with lakes, but they're squished so far down here because we have some very high concentrations. So that kind of automatically scales the graph. So it'll squish your standards way down there because there's so many high E. coli samples where the results exceed the standard. But at least you can see them in comparison to the standard and you know that, well, yeah, this one's probably got a problem with E. coli. And then to me, one of the more interesting graphs on rivers, but this graph can also be available on lakes if there's mercury data from within the last 5 years. These are cool because you can hover over the dot and you can see the length of the fish as well as the fish species. So it can kind of give you an idea of what species of fish and what sizes of them you would want to eat. Because mercury, mercury can be toxic. That's why we have standards for it. It bioaccumulates in fish. That means that the top predator fish have more because the mercury works its way up the food chain and accumulates in the top predators. And it's dangerous to small children, babies, and unborn babies that are still not born yet, because it has a lot of toxic effects on developing brains. So that's usually the people that are most concerned about it. When my wife was pregnant and I had 2 little babies at home, it's something that we thought about. And so you see there's a standard line at 0.3. That's not the same thing as the standard for a fish consumption advisory. You've probably seen those signs along lakes. A fish consumption advisory is issued when you have fish with concentration greater than 1, which would be way up here somewhere. So right here, the very top one, we've got a walleye. The concentration is 0.41. That's over the standard of 0.3. It's issued by the EPA. So maybe you're a little concerned about this fish. You see the length, 568 meters. That's about a 23.5-inch walleye. It's a pretty big fish. So maybe you don't want to eat those 23 inches. Those are over the standard, you know. We've got another one here, 499 millimeters. What's that? Maybe a 20-incher or so. It's still kind of on the border there. And as we go down, we see some other walleyes up here. Oh, they sampled a carp. I wonder how many people eat those. Got another nice sized walleye that's close to the 0.3. As we go down, we start to see some other species in here. Oh, there's a channel catfish, another channel cat. You start to get the idea here. Hey, maybe I want to eat the channel catfish out of this river instead of the walleyes. The reason that the channel catfish are lower is because channel catfish are not top predators. They're omnivores. They eat everything. And so they consequently don't accumulate as much mercury. So this is really helpful if you're concerned about mercury. You can see the species and the size of fish that, you know, might be over that standard of 0.3. Let's check a couple more things here real quick. Let's look at the impairments. So we clicked on support status, impairment parameters. We go down, yep, there's mercury because we had a fish that was over the mercury standard. There's E. coli because we had, boy, a lot of E. coli samples over the standard. And oh, here's total suspended solids as well. We had some TSS samples over the standard. So this is how you can kind of get an idea of how to use this website to figure out if your water body is impaired, to see what the actual results are, and kind of just how to navigate it. Monitoring data is the same thing as the lakes. Any sampling station on the segment 8 of the Big Sioux River is going to be listed here, and you can click on view data. Projects and reports is the same as the lakes, which I won't get into too much. TMDLs, other old project reports. So that's really about what I got on navigating WQ Map. And I can throw it back to you. If you want to, I don't know if you do want to do any questions with that now or wait till later.
Yeah, well, if anybody has a question, just to unmute real quick. Okay, I am not seeing any hands raised or hearing any questions. So I guess we'll throw it over to Jordan then.
All right.
Okay, give me a second here.
And I'd just like to introduce Jordan. Jordan works with me in the Jordan works with me in the Watershed Protection Program. She's a new scientist that started here this spring. She was an intern with us for a couple of summers, and she's going to be helping me out on the volunteer stuff so that I don't get overwhelmed with stuff, because I got a lot going on. And Jordan's going to be a great asset and a great help to all of us. So that's Jordan. Go ahead, Jordan.
Thanks. Can everybody see that first off?
Looks good.
Okay, so now we're going to talk about how you can interpret some of your water quality data. And first we have this table. Well, no, doesn't want to work. There we go. That should have gotten emailed out to you guys, and it's the list of beneficial uses that each water body in South Dakota can be assigned. And we're going to talk about a few of them that are highlighted in blue today, and those are the parameters that you sampled. And you can see that there's multiple different numbers listed for the standards that they need to have to uphold each beneficial use. And then there's a few other things we'll talk about today that have more difficult standards to understand, and Jesse will kind of explain those.
Yeah, and if you look at that table, you see like it's kind of complicated. Like water quality standards are way more complex than, okay, there's one number, and if it's higher or lower than that, it's a problem. It's way more complex than that, unfortunately, but that's just the way that it is. So one thing that I'm going to mention here is there's kind of two types of water quality standards. There's numeric standards, which, as the name implies, are based on a number or a couple of numbers or something like that. And those, we're E. coli and TSS are in microcystin are great examples because they're fairly easy to understand. Ammonia, not so much, because it's an equation that pulls in other things like pH. But now narrative standards, this is where it gets weird. As the name implies, narrative standards are based on language and words. And ours in the States say things like, the lake can't be so green with algae that you can't swim in it, or that it's causing fish to die, or you can't have your whole river covered in an oil slick. And those seem like they'd be pretty straightforward, but they're really hard to kind of implement. But something interesting has happened with these narrative standards. You'll notice on the numeric standards, we don't have anything for phosphorus or total nitrogen or chlorophyll, which are all very important things for water quality health. So EPA kind of pulled a fast one, which I have to tip my hat to them. It was pretty clever. They said, well, your state isn't enforcing your narrative standards because we know that your lakes get really green. So we're going to make you apply some numbers to your narrative standards. And so we've been working with EPA on this process for the last, 6, 7, 8 years, where we've developed standards that are based in numbers, at least for the most part, for total nitrogen, phosphorus, and chlorophyll A for lakes and streams. So we'll get into that here in a few minutes when we talk about those individual parameters.
So first we'll talk about E. coli. It's a bacteria that's commonly found in the intestinal tracts of humans and animals. So it's an indicator of fecal contamination in water bodies. And when it's ingested, it can cause gastrointestinal and respiratory illnesses. So we have two standards relating to E. coli in streams and water bodies. And one of those is for limited contact, like what you would typically do on certain creeks and streams, and that would be fishing, kayaking, where you're not fully in the water. That standard is 1,178 colony forming units per 100 milliliters, and that's the daily maximum. And then we have immersion recreation, which is fully swimming in the water body, usually on lakes or big rivers. And the standard for that is 235 colony forming units per 100 milliliters as the daily maximum. And then for E. coli, there's many potential sources. Most of it comes from livestock and agriculture. It can also come from humans, from septic systems that may be leaking, or wastewater treatment plants. And then it can also come from certain animals, wildlife, and pets. Then we have total suspended solids. So that is all the organic and inorganic matter that won't pass through a filter. And you can see a picture of some of those filters with different amounts of, it's basically dirt that won't pass through. So in South Dakota, that comes from soil erosion and runoff. And we are concerned about this because it can impact fish life negatively. It can cloud up the water, and it makes it harder for them to see where they're swimming. And it can also settle into the gravel beds that they use for spawning, so it can affect their population. It can also, because it makes the water more cloudy, it reduces the depth that sunlight can reach into the water column, so it can impact plant life as well. And there's multiple suspended solid standards, and they all relate to fish life. So cold water fisheries would be Rapid Creek or Spearfish Creek, and they support more fish life and a lot of trout, so they have lower suspended solid standards. You see the 53 and the 158 milligrams per liter. And then warm water fish life propagation is in the Big Sioux and James River and Missouri River, and they have a higher suspended solid limit because there's less fish to support there. And then you can see the highest one is on water bodies where there's only sometimes fish.
And one thing that I'd add here is that those the warm water fish are more tolerant in most cases of sediment in the water as well. Whereas trout and those cold water fisheries, they will not last long. But like warm water fishery, you know, the Missouri River, those catfish do just fine. Or in the James River, the Big Sioux, where it's even pretty cloudy with sediment, they can handle more sediment than cold water fish like trout.
So an example of that would actually be the White River. So even though it has a suspended solid average of 3,899, you can still find fish there. And then we also have a picture of Rapid Creek, and that has an average of 10.8 milligrams per liter of suspended solids. So you can see the big difference in South Dakota waters right there. And next we'll move into nutrients, which should be nitrogen and phosphorus, which are typically applied as fertilizers in South Dakota. So we have a picture of the nitrogen cycle right here to show both that nitrogen exists in many forms in the environment, and it can also switch between all of those forms very quickly. We monitor multiple different forms of nitrogen for that reason. And it is commonly applied as a fertilizer, but can also come from organic nitrogen, which is just anything that comes from a living being. So first we have nitrate and nitrite. Nitrate can cause illness called blue baby syndrome, which is when you have too much nitrate in your blood and it reduces the amount of oxygen you can carry in your bloodstream, so you'll turn blue. And to protect people from that, we have a domestic water supply standard of 10 micrograms per liter. And there's also a standard for fish, wildlife, recreation, and stock watering, which is 88 milligrams per liter for the daily maximum.
And I'd just like to point out that 88 milligrams per liter in my whole career doing water quality science, I don't know, I've been around here, what, 15, 16, 17 years. I've never seen a sample that was 88 milligrams per liter. I don't think that there's one in our entire database. I think I looked and the maximum that I saw was like 45 or something. So that standard, while it is a real standard that's on the books, it might as well not even be there because it's completely useless. It's so high that you'll never see that. If it gets to 88 milligrams per liter nitrate, like you got a serious problem.
So then with that, we process nitrate and nitrite in the same sample because it flips back between those two forms very rapidly. And nitrite is also linked to various human health problems. And then we also have nitrogen as ammonia as one of the parameters we look at, and it can cause mass fish die-offs, you can see in this picture, and that's because in high concentrations, it's toxic to aquatic invertebrates and fish. And it can also be converted to nitrate pretty quickly. And that's an equation-based standard, as Jesse mentioned earlier, that takes into account pH and other factors.
And one thing I'd point out here real quick is particularly in lakes, you don't usually see much ammonia. Same thing for nitrate and nitrate. If you do see some, it's probably going to be fairly small amounts in the spring or early summer. The exception to that is where you just have a lot of runoff that contains nitrate, or ammonia. But so if you see a little bit in your results for a lake sample, and by a little bit, I mean like 0.3, 0.5, less than 1 milligram per liter. Those kind of happen and it's nothing to be alarmed about. You don't usually see any ammonia or nitrate in lake samples later in the summer, but that's just kind of generally speaking. There's certainly exceptions to that. But one quick thing to point out about nitrate in rivers is in the southeast part of the state, especially the Big Sioux Basin and parts of the Vermilion Basin. We see some very high nitrate concentrations. It's like in the Big Sioux, you'll see results over that 10 milligrams per liter standard for the domestic water supply. That's a drinking water supply. And part of the Big Sioux River there by Sioux Falls is actually used as a drinking water supply, or can be used under the law. So that's kind of the results that you would expect to see, next to nothing throughout most of the state for nitrate, and ammonia. In the very southeast, you'll tend to see more.
And then one of the other ones we look at is total Kjeldahl nitrogen, and that is the sum of organic nitrogen and ammonia. So organic nitrogen in a sample would typically be little flecks of algae or other small plant matter that you'd find, or small
Like
Invertebrates.
Yeah.
Zooplankton, yes. So that's the kind of stuff we can see from that kind of sample. And then also on WQ map, total nitrogen is the result that's displayed there. And that's the total Kjeldahl nitrogen plus nitrate plus nitrite. And for some reference, we have the Swan Lake average is 3.28 milligrams per liter, and Deerfield Lake has an average of 0.2 milligrams per liter. Swan Lake is in an area with lots of agricultural activities, so it would have higher nitrogen being applied to the fields in more fertile soils. Deerfield Lake is in the heart of the Black Hills, and it's surrounded by a lot of national forest land, so there's less fertile soils there. It's all rocks and trees and stuff, and they do some cattle grazing, but very rarely. So that's what you can expect from those kind of different land areas.
And then that Swan Lake watershed, real quick, if you don't mind, Jordan, there's also a lot of drain tile. And if there's a lot of drain tile in your watershed, as we see in eastern and particularly southeastern South Dakota, that's how you end up with more nitrogen in your waters. So that 3.28 for Swan Lake for total nitrogen, that's quite high. And one other quick thing, I don't know if we mentioned it, but TKN or total Kjeldahl nitrogen, that's all the organic nitrogen plus ammonia. So that's why total nitrogen doesn't mention that ammonia is part of it. It's part of the TKN. So go ahead. Sorry about that.
Good points. So we'll also talk about phosphorus, and that's another chemical that's commonly applied as a fertilizer. It can have other sources too, from leaking septic systems or discharge from wastewater treatment plants. And as a fertilizer, it can also contribute to excessive algal and aquatic plant growth. So to look at some of the numbers on phosphorus, you can look at Minot Lake, which is also in an area with more fertile soils and more agriculture activity, that has an average of 1.268 milligrams per liter. And then again, Deerfield Lake out in the hills has 0.016 milligrams per liter on average for phosphorus.
And that value for Minot Lake, that's really high. Like if you're even approaching 1 milligram per liter in your lake for total phosphorus, like that's really bad. You might see that amount in some streams on occasion, especially in the southeast part of the state. But if you see anything around or over 1, it's probably a lake that's going to have a lot of algae blooms. Okay, this slide. I'll try to unpack this baby here. So this is where we get into some narrative standards. And like I said, they're not simple. So what we're looking at here, this is the narrative standards for nitrogen and phosphorus for streams. These standards only apply, you see the little map in the top right, to the 43 there, that's kind of the western prairie of South Dakota. And the 46 on the right in the orange, that's the eastern kind of temperate plains, the glaciated part of eastern South Dakota, or at least part of it. And so in that little table on the bottom right, you see there's 4 different values there for those regions, one each for phosphorus and nitrogen for each region. And how this whole system works is if a stream has phosphorus or nitrogen concentration above those numbers in the table, then we go to our nightmare of a flow chart on the left. And I'm not going to try to walk you through this whole thing because every time I try to do it myself, I have to stop and think about it for about 10 minutes. But the gist of it is that if the concentration of those nutrients in the stream is greater than those numbers, we go to this flow chart and we find out, okay, is there enough data to actually answer the question of whether it's impaired or not? Is the stream wadable? Because this only applies to wadable streams. So not the large rivers, not the Big Sioux, the James, none of that stuff, not the Missouri, it's just the smaller streams. And then we look at the fish and the invertebrate communities. And this chart right here is the main reason why I included macroinvertebrate collection in the volunteer program, is because you can help out with this whole system by collecting macroinvertebrate samples, because if the stream is above those values for phosphorus and nitrogen, we look at the fish and the invertebrates and we calculate a score from the data from their communities. And it's a 0 to 100 score. It's called an IBI, or Index of Biotic Integrity. And it's a way to make it simple to understand complex data. So we get the score, it's 0 to 100. If both the bugs and the fish look good, like their scores are greater than 50, we say that it's not impaired. The nutrients must not be impairing the aquatic life community there. If one score is below 50, say the bugs are below 50, but the fish are above 50, then we go to a tiebreaker. It's a habitat condition index score, which is a whole nother thing. It's actually a coworker and I developed that, a habitat condition index, and it's again a 0 to 100 score. And if your habitat then is good, you say, okay, the stream isn't impaired, and we move on. If the habitat score is below 50, we say it's impaired, and we list it as impaired on the 303D list of impaired waters. So it's a very complex way of trying to figure out if a stream is impaired for nutrients or not. Go ahead,
So
Jordan.
next we'll talk about chlorophyll A. It's a pigment that's commonly found in various types of plants and algae. And you can see on that chromatography strip to the side there, it splits up the different kinds of pigment that you can find in different algae cells. And chlorophyll A is right at the top there, and it's bright green. So chlorophyll A is a response variable. So by the level of chlorophyll A, we can kind of guess what amount of algae is present in the water body. And from that, we can kind of have an idea of what the toxic algae will look like. So because of that, we have less than 10 micrograms per liter as a low risk of developing negative health effects on humans. And then between 10 and 50, that's a moderate risk. And then anything above that 50 micrograms per liter of chlorophyll A is a high risk of developing negative health effects in humans. And I have a graph of, first, Jesse's going to talk about some of the standards for chlorophyll A.
Oh yeah, and so this goes back to those lake regions that were on WQ map. And so these values on this little table, we have a different standard for chlorophyll for each region, because the lakes in each region are different. So the Western lakes at 14, they don't get too green. The Eastern lakes at about 38, the Northeastern at about 50. And then we split the Black Hills lakes into large and small. And the large Black Hills lakes are Pactola, Deerfield, and Sheridan, and the small ones are all the rest. So this is actually a pretty easy standard to understand, because it's actually just a single number for your lake. One thing that I need to point out here, though, the standards for Eastern and Northeastern lakes are going to change in the spring of 2022 when we release the next integrated report. Because if you remember back to the last slide, if you're over 50, you're at a high risk of negative health impacts from cyanotoxins. Well, we can't really have a standard that's right at 50, because that's probably going to get people sick without the lake even being impaired. I mean, it's at least in the moderate risk category. So what we're going to do is these standards, we've been working on this with EPA for a long time. These are going to end up being about 25. And then there might be a couple standards for like shallow and deeper lakes, but that'll change here. So there are chlorophyll standards. Once we get that change done, I want to put lines on the graphs on WQ map so that you can see how your chlorophyll data compares to the standard. I didn't have them put on there originally because I knew that these were going to change, because we're going through that process already.
So now we can look at some of the volunteer monitoring results for chlorophyll A, and these are all from lakes. So you can see there's a lot of them that are in that moderate risk zone between 10 and 50 micrograms per liter, micrograms per liter. And then there's a handful of them that are above in the high risk category, and one or two that are below the 10 micrograms per liter.
And those two up there around 200, those are really high, like really, really high. You know, anything over 50 is really high, but you get up there around 200 or 300 and you're talking astronomical.
So that brings us to microcystin. It's the most common cyanotoxin in freshwater lakes. So it's a hepatotoxin, which means it predominantly affects the liver. If humans are exposed to it, you can develop abdominal pain, headache, sore throat, vomiting and nausea, dry cough, diarrhea, blistering around the mouth, and pneumonia. So you'll definitely know if you're sick. It can also kill livestock and pets that drink the affected waters, and it is more harmful to smaller animals like livestock and pets because they have smaller livers, so they process the toxin less well than humans would. So the standard from the EPA we've adopted is 8 micrograms per liter for microcystin, and that picture on the slide is a picture of Lake Herman, and which had a microcystin result of 66.8 micrograms per liter this summer. And then here is a graph of all of the microcystin results that you guys collected with the line for the standard in orange right there. You can see those 8 or 9 lakes that are above that standard. We issued HABs notifications for those on the harmful algal blooms interactive map, which Jesse will talk about now after we do some screen switching.
Yeah, I'm just gonna walk you through this real quick because I thought if I'm gonna show you a WQ map, I might as well show you this one too, and it'll only take me a minute. So let me get it opened up here. All right, can you guys see my screen yet? Can you see it, Jordan?
No.
No? All right, let me try again. Oh, there we go. I have to press share. All right, see it now?
Yeah.
All right. So again, a disclaimer, it always has to pop up. You can read it if you want to. So this is the HABs map. HABs is harmful algal blooms. Nobody wants to say harmful algal blooms over and over again, so we abbreviate it to HABs. I'm going to walk you through a couple things here real quick. Another great help section. I wrote that one too. I created WQ map and this one, so if you got questions, you can hit me with them. You can read the help menu if you want. We'll start over here with the legend. Red flags, that's for a HABs notification. If there was a sample on a lake that was over that 8 micrograms per liter, it gets a red flag. And we see we've got quite a few of those this summer, predominantly in the eastern part of the state, where we have fertile soils and intensive agriculture that results in more nutrients that flow into the lakes that cause algae to grow and the algae to produce microcystin and other cyanotoxins. We've got the purple stars here. We've only got 2 sizes. We've got big ones. Those are for samples over the standard of 8 and then we've got small ones for samples that were below 8. So basically, if you see a big star, you want to worry about it. If you see a little star, you're not so concerned. The red balloons, those are algal bloom reports. I'll show you those in a sec. And then the green dots, we got 3 different sizes. These are where we actually look at the algae cells, count them up of each kind, and we count up all the ones that produce toxins. There's 3 different risk levels here. It's kind of like chlorophyll, but different numbers. If it's over 100,000, that's high risk. If it's 20,000 to 100,000, it's moderate risk. And if it's below 20,000, it's low risk. And then those are collected from the center of lakes. And then we have this algal toxin results 2020. This is last year's sampling from the centers of lakes where we tested for toxins. And we've got over 8 is the big ones, 0.1 to 8 is the medium sized, and a non-detector, basically we didn't find any, are the very small ones. Real quick thing here, this button up here is the layers. As time goes on, I turn off the old layers and I add new layers for the new years. But you can always go back through time. 5 years from now, you can go back and you can turn on the 2019 toxin producing algae or the 2020 algal bloom reports, and you can see what things were like in that year. I intend to leave those there forever. I leave the 2020 stuff on there for a while if I think it's still relevant and doesn't clutter up the map too much. But once we start sampling next year, these will get turned off and we'll mostly have 2022 information then. So we'll just zoom in on a lake real quick. We'll go into Lake Madison because in terms of algae blooms, it's got a little bit of everything going on. So let's just start on the left side here. We've got a big purple star. That's 115 micrograms per liter of microcystin. That's well above the standard of 8. That means it gets a red flag for a HABs notification. And you can see here, I provide a little text so that you can understand what those are. They last for the whole year because we assume that if a lake gets above 8 micrograms per liter microcystin at one time, it's probably going to do it again because it has the conditions that that would facilitate that. We've got some small stars where we had, results that weren't over 8. And you can see in the little pop-up tables the date and the result. It's organized a little differently than WQMAP. And then there's a little graph at the bottom and some info about that standard of 8 micrograms per liter. We go in the middle. So we've got a green dot. That's our toxin producing algae results. Remember, if it was over 100,000, it's high risk. So when it was sampled on July 23rd last year, it was 160,000. In August, it was 109,000. By September, it finally got down out of the high risk category to low risk. But if you forget what those risk levels are, they're listed right here in the text. So you can get an idea of what's good and what's bad. And there's a little graph that's not very useful. And then if we have more than one symbol in one place, we got 1 of 3 here. We used a little arrow to go over to the side. We can see the mid-lake algal toxin results. Madison had a 21.6. That was the highest one that we got in the middle of a lake last year. And information about the HAB notification. Last thing I'm going to show you are harmful algal bloom reports. And so again, it's a little pop-up window. This was one where we received a report of a dog becoming ill after playing in the water. Some samples were collected, but it was a few days after the event with the dog, and the results were 1, so they're below 8. But we also link to pictures on these algal bloom reports, and we list any results of sampling as well. So if you click on the more info, it shows you a picture. And looking at that, yeah, I believe that dog probably got sick from, consuming some algae. And then there's one more picture there. It's a little bit different one. So that's how you can use that to look at algal bloom reports. And that's, but one more thing. There's this thing down here. This is your attribute table. All the information presented on the map is in a table format here. There's different tabs to look at the different layers. And if you go to options here, you can export this data to a CSV file, which it'll probably show up in Excel on your computer. And that way you can actually pull the data out of here and work with it yourself if you want. You can do some filtering and things like that as well. So that is the HABs map.
Okay. Wow. There was a lot. And I asked people to put questions in the chat. So far, nothing's come out. But if you would like to unmute and share a question or a comment, please go ahead and do so. And while we're waiting for folks to unmute, I have this is probably a whole nother webinar. But okay, so you were showing us, the data that you collected that, was up here, but every once in a while, like that, what was it, that 200, and it was like way down here. What do you have to do to get the data back up here?
That is a really great and complicated question. Every situation is different, but the gist of it is you have to reduce the sources of pollution. And that's actually one thing that we figure out in TMDLs is A, what are the sources of pollution? And then B, how much do we have to reduce them to meet the water quality standards? And then C, how do we actually reduce them? So it might be things like putting in riparian buffer strips or renovating a feedlot, or working with a local, municipal or industrial discharger to change how they do things. Basically, we can be as creative as we want. I wrote one TMDL once where my plan to fix up some nitrate coming in from some groundwater saline seeps was to plant a lot of alfalfa because it has really deep roots and it intercepts the nitrate laden water before it comes out the hillside. So, I mean, you can, basically, we think of everything that we can that's going to work.
Okay, any other questions for Jesse or Jordan? Well, you know where to get a hold of them, and I'll also put their contact information in the show notes on the YouTube, and we'll send that out. So if anybody would like to reach out to them that way, we can certainly make that happen. We can make that connection. We are going to be monitoring again next year. The data is looking good. The money is looking good. So I'm the money person. My program is the one that's paying for all this, and I'm very excited to see this happen. I've got started in this whole field working with a water quality monitoring program in the late 1990s. So it's really good to see it grow and to see everybody participate and to see the data coming out. One of the things we struggled with back then was how can we communicate the data to the people who collected it? So this is really, really, really exciting. So thank you, everybody. And Jesse, did you have something else?
Looked like Deb, did you have a question or something?
Oh,
Well, I was just wondering about Lake Madison with their algae bloom. Did they go on any special program that helped to get them off any kind of impairment or?
So we've actually had some discussions with some local like lake cabin owners and stuff, and they're kind of in the beginning stages of getting organized to work with local government and state government, et cetera, to maybe address the issue. Addressing those issues almost always starts with local support and local coordination, because you really, if the people there don't really care, you're not going to ever solve the problem. The people around Lake Madison do care, and we get quite a few calls about it. The hard thing is it's very, very difficult to fix that problem. Now, Lake Mitchell has been fairly aggressively addressing their issues with algae blooms, and perhaps what they're doing can act as a model for what's going on Lake Madison and some other lakes in the state, because Mitchell and Madison are kind of similar in the sense that there's a lot of money around those lakes. So there's a lot of will for them to be cleaner because people want to enjoy their lakes. So Madison hasn't really done much of anything yet. I think that may happen down the road. Often all it takes is one person with kind of a fire lit under them, and they start going and banging on doors and calling people, and next thing you know, there's a project in place and funding's been secured, and things like that happen. But we do at DANR, we kind of do more broad scale projects where we're working in I think the Central Big Sioux right now, and we're working in the Lower James Basin, but we're kind of working in a more general sense of generally trying to improve water quality. We're trying to see measurable improvements in the lakes and streams, but there's a lot of lakes and streams in South Dakota. So outside of a desired focus from folks like local folks on the ground, we kind of work more generally. Not always. We focus on individual water bodies on a lot of occasions as well, but that's not going on so much right now. Does that answer the question?
Yeah, thank you, Jesse. And thanks for that map. Nice work on that. I'm sure that's taken a lot of time putting that together.
Yeah, they're fun though. Does anybody have anything else that they'd like to ask or add? Looks pretty quiet. Well, Ann?
well, I think we can call it a show. So this is awesome. Thank you so much.
Oh,
Thank you.
Hey, one more thing before you guys log off. Later this fall into the winter, we're hoping to get together with you all again to talk about kind of more in-depth data analysis, and to kind of throw out the offer, if you want us to put together some materials like graphs, infographics, things like that, that would be helpful for you to communicate with your groups or others that you're involved with, or just for your own information, we can set that kind of stuff up. So we'll be in contact with you about that later on.
Good. Thank you.
Yeah, you're welcome.
Mhm.
All right.
Okay.
Well, have a good evening, everyone.
Yeah, you have a good evening
Yep.
too. All right.
Thank you.
Thank you.